Thank you for the introduction. Hi, everyone. Like Ashley said, my name is Vicki. I am a software engineer at Interstellar, and today we're going to be talking about a topic that I think is off the chain, just scaling blockchains in Go, and the joke will only get funnier as we go along, I promise. So a quick overview of what we're going to talk about today. First, I'll talk a little bit about why we should even talk about blockchain scaling, which may be a question that some of you are wondering, maybe not, which is why you're in this room. I'll give a little bit of an overview to the space in terms of sort of what the solutions to scaling blockchains are, and then I'll talk about two projects that we work on at Interstellar. One is payment channels through Starlight, and the other is pegged sidechains through a project that we call SlideChain. And then I'll give a little preview of sort of what we're working on for the future. So the first question, and the most important one, is why should I care, right? Like, why should I care about blockchains, about blockchain scaling? And, a lot of people have questions. It's been 10 years since Bitcoin was invented, and many people think that there's nothing really to show for it. And for today, we're going to sort of put aside a lot of the economic and societal arguments that people use and focus just on sort of the technicalities. And so if you believe that there's promise in blockchain technologies, which there may or may not be, there's also a really existential threat, which is that blockchains don't scale. And this is a problem that's going to have to be solved before they can be used for anything on the order of the things that people are imagining in terms of real-world financial systems. And this might, to some of you who are familiar with blockchain technologies, this might make a lot of sense, and you're like, yeah, for sure they don't scale. This is what the whole community is talking about. But if you want to understand why this is true, it's quite simple if you look at the anatomy of a blockchain. So a blockchain is a chain of blocks. And a block is usually formed of a series of transactions. And so how these transactions are represented differs in different networks, but you can think of it as just a list of, who's sending money to whom. And we chain these blocks together using something called a hash pointer. So each block contains the hash of the previous block. So when you add a new block to the chain, you're basically committing to the entire history of everything that came before. So no one can go back and pretend that they sent you $500 when they only sent $5. And so this is all really great, but anyone could implement this, so why is this super revolutionary? And really the big sort of breakthrough in blockchain technologies is to do this in a way that's decentralized. And so what that means is that we have a network of many different nodes that are all connected to each other, and this network validates every block on the blockchain before it's added. So this means that everyone comes to consensus about the history of the transactions that have happened, and there's no single trusted authority. But in order to do that, every single node on the network needs to see every single block, and that means that every node needs to see every transaction. And that's the existential blockchain scaling threat, because that model is not scalable. If you think about the number of transactions that happen every day, the number of times you swipe your card multiplied by all the people on the earth, there's no way that you can maintain a decentralized network that's actually actively watching for all of those. And so in terms of the numbers, how this works out is what are called the block confirmation times, or the amount of time it takes to confirm a transaction on different networks. On Bitcoin, it's 10 minutes. You can do a little bit better. On Ethereum, it's 10 to 20 seconds. And on the network that we work on at Interstellar called Stellar, it's about 5 seconds. And these times are, pretty fast, but in terms of a lot of the applications that you want to build, 5 seconds is a super long time, right? If you think about having to wait for a transaction to be confirmed for 5 seconds, it's like an eon in computer years. And so there are some other challenges, because nodes are all run independently, making software updates is really tough and requires a long process. You might hear about these things if you follow Bitcoin news. They drag out for a really long time. And also, since we want networks to be decentralized, we need to keep the cost of running nodes to be pretty low. And so that also introduces additional constraints. But these are sort of minor in comparison to the real problem, which is just that because of the decentralized setup, all nodes need to be seeing all transactions. And so we need to find ways to make that scale without compromising trust and safety on the network. So this seems kind of bleak, right? You're like, oh man, blockchains are screwed. But there are things we can do. And so there are basically two schools of thought or approaches to blockchain scaling, and you can think about them in two layers, like a layer cake. The first layer is about building more functionalities into blockchains themselves. So this is like thinking about more compact data representations for transactions, trying to get that confirmation time from 10 minutes to 5 seconds. And the second layer, excuse me, is about developing protocols that live on top of the blockchain. So it's thinking, we have this underlying system which requires consensus, but how can we actually make it so that we can confirm more transactions without everyone having to see them? So you can think about it as, the first layer being the groundwork and the real infrastructure, and then thinking about this network of off-chain transactions on top of that, trying to make it so that we can process transactions without having to really confirm them publicly. And so now the question is, okay, blockchain scaling makes sense. We have these approaches, so why use Go? Why talk about this at a Go conference? And I think there are a couple of compelling reasons. One, drink some water, is that Go has really simple, lightweight, native concurrency, which is great because for a lot of these applications, you need to be running a lot of processes, you need to be watching the network and responding to it, and Go makes that easier than almost any other programming language that you would have at your disposal for developing blockchain applications. There's also really easy cross-platform compilation, which is awesome when you want to write software that you need to be able to run on a variety of hardwares and devices in order to maintain your network. There's really good networking support, which again is great because all of these are dealing with messages coming in and out, submitting transactions, watching for them. And also, Go is like a great programming language to use. It's easy to understand. There's usually pretty low programming overhead. It's really good for doing open source projects because people feel comfortable contributing. So all of these are reasons that we at Interstellar have chosen to write a lot of our blockchain projects in Go. So now we'll get into the meat of it, and the first project that I'm going to talk about is called Starlight, and it's an implementation of what we call payment channels. So the idea behind payment channels is we want to move on-chain transactions into private payment channels to allow people to pay privately and also quickly. So for example, what this means is that if I am trying to pay my friend Alice and we pay each other really often, we could just conduct these payments privately by sending like text messages to each other about how much money we owe each other. And then at the end, once we've settled, we can publish that to the blockchain. So instead of publishing our 100 messages between each other, we only end up publishing one on the network. So another example is I maybe want to start a company called CryptoFlix, which is Netflix, but with cryptocurrency. And the way that I want this business to run is that I'll charge people 1 cent for every minute of content that they watch. So my first user is watching. I'm really excited. And so what's going to happen is that I've set it up so that Alice sends 1 cent to CryptoFlix every minute, and she publishes that transaction on the blockchain, and everything is great. Except for there's a 4-minute delay in between when she submits a transaction when it gets confirmed, which means that she could steal up to 4 minutes of content by not paying for it, and I wouldn't know because the transaction hasn't been confirmed. So I don't like this very much. I'm not too excited. So I decide to move to a payment channel model. So now instead, every minute, Alice sends a message to CryptoFlix saying how much money she owes. So she says, I owe 1 cent, 2 cents. After watching Avengers Endgame, she owes me $1.82. And then we close the channel and we publish one transaction of the sum total amount that she owes me. Of course, this isn't super great either because she could always just publish that a transaction with only 1 cent, and then she's watched the whole movie and she's stolen all my money, and so I'm not super stoked about that either. So instead, what we do is we actually sign transactions that we pass back and forth for each of the amounts. So these messages are actually a transaction that Alice is sending to me and that I'm signing, but that's not submitted to the network until the very end, until we close the channel, and then we publish the total transaction. And so this way, if she tries to cheat me out of my money and send a message with less value than she actually owes me, I can publish a valid signed transaction with the total confirmed amount and confirm that to the network. And I know that we've agreed on this amount. Even if it takes minutes to settle, I know that there's no way that she can cheat me out of my money. And we've also reduced a lot of the transaction volume on the network. So this is a project that's called Starlight, and you can see it's all open source, and it's built on Stellar, which is a public blockchain network like Bitcoin or Ethereum. The key sort of selling points of Stellar are that it supports multiple assets, so you can issue any assets that you want onto the Stellar network. They make that really easy. there's pretty fast settlement time, and there's good basic smart contracting capability. It's not meant to be sort of a world computer in the same way that Ethereum is, but you can sort of trigger some computations with transactions, lock funds into escrow, and unlock them later programmatically and do basic operations like that. So in Starlight, for our implementation, each party in the network runs what we call a Starlight agent. And agents respond to 4 different types of inputs: user commands like send someone money, messages from other agents, transactions on the network, and timer events. And so for each channel that an agent has open, they maintain a state machine of sort of where that channel is at the moment, if a transaction is processing, if it's confirmed. And so what this looks like in Go is that each agent has an HTTP client that we use for requests. It has a persistent task queue that we use to queue up things like sending messages or submitting transactions. We use a lightweight in-memory key value store to store all of the data, so it's really easy to boot up, but you can also persist state across agent restarts. And then we also use we have a map of cancelers so that we're able to really easily clean up all of the Go routines that we start for each agent, and we map those to the channels that they have open. Since an agent can have open many channels, so we want to be able to really easily start up and close channels. And so each channel also has some state, and these are designed to be serializable to and from pure data, so we can store them in our in-memory key value store. So we maintain sort of the state machine state, the counterparty address, the amounts, the pending amounts that are being sent, and then also these signed transactions that are being sent as the messages back and forth. In terms of our task queue, this is how we issue all of the tasks that are going to be sent out by the agent, so we just queue them. And so we have a basic interface where any task can implement this run interface, so whether it's a message or a transaction, all we need to do is run it, and that's how we make sure that, even if the transaction fails on submit because you don't have high enough fees, that we can just start a Go routine to run this and don't have to worry about it, which makes it really conceptually easy to think about. So here, this is our implementation for sending a message to another agent. And so when we want to initiate a payment, we just add this to the task basket, and then this will continue to run the task until it completes successfully, so that our agents are sending out messages and submitting transactions, and we don't have to worry about them, losing anything. And then in terms of watching channels, when we start up a channel, basically we just start a number of Go routines to watch the account that we hold on the network, to poll for messages from the other side, and also to send keep alive messages. And so all of this, you can sort of see why Go is really nice, because it's super easy for us just to start a bunch of Go routines to manage all of the work that agents need to be doing to watch and submit messages on the network. And so now, this is a demo. So here you can see I have 2 Starlight agents, and I'm sending money back and forth between them on the 2 sides. And it transfers basically instantly, because all that's happening is just messages are being sent back and forth over the internet. And then when we close the channel, this longer time is actually when a transaction is being submitted to the network, and then we have to wait a couple of seconds for it to be confirmed. But you can see that the payments in between parties on the network or parties in the payment channel is like instant, but the closing time takes a little bit longer. So in terms of looking towards Starlight, we've implemented this 2-party back and forth payment channel model, but that doesn't map super well onto a lot of the real world applications, as you can imagine. So sort of the next step is to build out a network where you can route payments through different channels and do multi-hop payments. So I could pay Charlie through Bob. And so that would allow a more full-fledged network, and we can interoperate with other frameworks like Lightning or Interledger that you might have heard of that are also sort of projects in a similar space of thinking about scaling through payment channels. So to switch gears, another project that we've worked on at Interstellar in blockchain scaling land is called SlideChain, and this is a project implementing something that we call pegged sidechains. So a 2-way pegged sidechain is essentially a way to transfer value off of one blockchain network and into another. And so one analogy to think about it is if you were to go to a casino, you take your dollars or euros, and at the counter you exchange them for poker chips. And then you play games in Pokerland and can use those for various things. And then when you exit, you can also exchange your poker chips back for dollars or euros or whatever you had to start. And so here with sidechains, the idea is to be able to transfer value from something like Bitcoin to Stellar to maybe even another system that's faster and more scalable. And this is really nice because it sort of opens the door to be innovative in really fast ways without having to change things on the network and deal with consensus. So here for SlideChain, our sort of proof of concept is to try and export funds from the Stellar network into a project that we had used before called TXVM. And here we chose TXVM because it's a system that we built and that we're comfortable with, but ultimately the goal would be to transfer it to another network. Since right now in this implementation, TXVM, there's no consensus. You're basically just transferring your money and giving it to a person and then hoping that they hold on to it. And so we're using the trusted custodian model, which means that you have trust in whatever party is going to be doing the exchange. So this is not decentralized, it's not trustless in the way that a lot of other blockchain networks are. And so how it works is that when you peg in funds, first on the TXVM side, the side that you're transferring to, we create what we call a uniqueness token contract, which is basically a fancy term for saying that we commit to the state how much money is going to come in and to whom. So we're going to say, okay, Alice is going to get $5 US. And then on the Stellar side, we're going to make a transaction that sends $5 US to our trusted custodian and specifies in this memo field that it's meant for Alice. Then when the SlideChain custodian sees this transaction come in, they'll make an issuance program in TXVM that issues this $5 US to Alice and also consumes the uniqueness token. So we make sure that we're issuing this value only once and that we're issuing the amount that we expected. And pegging out is much the same process, just sort of in reverse. Instead of a uniqueness token contract, we make a temporary Stellar account because accounts can only be closed once. So this is sort of our idempotency guarantee. Then we're going to lock funds into a smart contract on the TXVM side. So if we see a successful peg out, we'll retire the funds, basically just wipe them out. But then if we see some failure case, then we'll actually just return them to the original owner. And then we go ahead and we have the custodian make a transaction to pay out the amount of money to the specified destination and also merge the temporary account atomically. So if we try to do this twice, the account has already been closed, so we know we can't peg out funds twice. And if there's some failure, then we'll unlock the TXVM side smart contract and the funds will be released. And so what the custodian looks like is basically we have we watch imports and exports to be able to signal to fire off Go routines when we see those events come in. And it also maintains a database, a Stellar address to be able to watch for transactions on the network, and then also some fields to manage the TXVM side submission, so a transaction submitter and also a block store. We launch a custodian basically by just starting a lot of Go routines. So all it really does is it watches for pegs in, and then it does the import process that we saw, and then it watches for exports, and then it does the peg out process. And that's essentially it. It's just watching for these different things that come in and out so that it can do the appropriate action either on the Stellar or the TXVM side. So in terms of watching and importing, basically we watch for a peg in, so a transaction that comes into us on the Stellar network, and then we'll signal to start a process that actually performs the import on TXVM. And again, this is super easy in Go, so it's really nice that we've done it this way. This would have been a real pain to do in something like Rust, so we were very happy with our choice here. And then also it's nice because TXVM is built natively in Go, so it makes it really easy to call code, to build transactions, to watch for things on the network. All of that is really, really easy and we can do natively. So here we are constructing the transaction and pushing some data onto it, so pushing the smart contract code, building the transaction, and then submitting it. So in terms of what's next for SlideChain, we're working actually on sort of, now that we have the pipe of how the pegs could happen, we're working on sort of what is it that we want to peg funds to. So we're working on building out viable sidechains for the Stellar network. And in particular, we have a focus on zero-knowledge systems and privacy. Sort of like I mentioned before, TXVM was just used as a proof of concept. It's not a public network. There's no consensus. So the ideal was never really to peg to that. but we wanted to see if this was a viable option for us to be able to innovate on different potential sidechains as options to make the Stellar network more private, more secure, and more scalable. So we've talked a little bit about some of the projects, but in terms of what's in store for the projects at Interstellar, sort of like I mentioned, we're focused now a lot on developing sidechains, and in particular on one project called ZKVM, which is a blockchain transaction virtual machine with zero-knowledge smart contracts and cloaked assets. So all of that is a lot of very long words for saying that we want to make a blockchain transaction system where you can pay people and there can be privacy about who you're paying and how much. So if you sort of think back to the scaling problem, having nodes on the network confirm every transaction presents a scaling problem, but also a huge privacy problem, because it means that every node on the network knows exactly who is sending how much money to who, which you can imagine is probably not something that you want. If you're using blockchain to process payroll, for example, everyone can see how much money people make. So there are a lot of obvious problems that this brings up. And so ZKVM is our attempt at using a lot of cool cryptography to build zero-knowledge systems where you can pay people and have it be confirmed and secure, but without the amounts and the assets being revealed. And so we've built this fun diagram because ZKVM is a project where a lot of the cryptography internals are being written in Rust so that we can take advantage of memory, safety, and really fast performance. But ultimately, the interfaces are going to be in Go for a lot of the reasons that I mentioned in terms of networking, being able to interoperate, just like fast, good development. So we have the Rust crab driving a motorcycle, pulling the nice trailer home with the gopher in it. But so ZKVM is all open source, and you can check out that and all of our other projects at interstellar.com/protocol. Oh, this is the same slide. So that's all I have. Thank you so much for listening. I'm happy to take questions. We don't have time for that, just kidding. Yeah, I'm on the internet. My handle is, I can go back to the first slide, actually. That's probably the easiest.
We have 15 minutes before the next session, I believe, so yes. So there's time for questions, just, unofficially.
That sounds good. But yes, you can find me on Twitter.
Thank you.
Cool, thank you.